Hello chemists, this is the Bales chemistry walkthrough video calculating the pH after a weak acid has reacted with a strong base. And in this example, we're going to look at what happens when there's an excess of base left over. We've done another video where there's an example of where there's an excess of acid left over after the reaction, and there's a link at the top of the screen. Now, if you haven't yet subscribed, consider doing so you make sure you get all of our content next week to help you with your chemistry studies. Now, there's a slightly different route to take when we've got an excess of base compared to when we've got an excess of acid, but they both start at the same point. We need to work out the moles of acid and the base. From this, we can then calculate the moles of remaining base, and once we've got that, we can turn that into a concentration. We need to remember here we've got to take the volume of the whole solution into account, so that's the volume of the acid plus the volume of base added. Once we've got a concentration of the hydroxide ions, we can then use the Kw expression. This is here, it's rearranged, so we've got Kw divided by the hydroxide ion concentration, and that will give us the H plus concentration. And then the last thing to do is to calculate the pH using the minus log of the hydrogen ions. This is the same step as if we're doing an excess of acid or an excess of base. Okay, so we've had a look at the steps we're going to take if we've got an excess of base, and now we're going to look at this question. A 30 centimetre cubed of 0.75 mole per decimetre cubed solution of benzoic acid reacts with 25 centimetres cubed of 1 mole per decimetre cubed solution of potassium hydroxide. The value of Kw is 1 times 10 to the minus 14. Calculate the pH of the remaining solution. So we're going to start off in exactly the same way as we've done before, where we're going to work out first the moles of HA present, and that's the benzoic acid. So we've got 30 centimetres cubed of benzoic acid. We're going to convert that to decimetres cubed by dividing it by 1,000, and then we're going to multiply that by its concentration of 0.75 to get a number of moles of 0.0225. We're then going to work out the moles of our OH minus. So potassium hydroxide is also a strong base. So we'll take its 25 centimetres cubed, we'll divide that by 1,000, and then we'll multiply it by its concentration, which is 1. And that gets us a value of 0.025. So again, we can see we've got an excess of the hydroxide ions over the moles of HA, but we need to know exactly how much. We'll make a short note of this here. So the moles of OH are in excess, and then we've got 0.025 minus 0.0225, which is going to give us an excess of 2.5 times 10 to the minus 3. Now we've got that excess, we need to work it into a concentration. So we'll scroll down a bit and we'll have concentration here. Before we can do a concentration, we need to work out the volume. So we'll take the 30 centimetres cubed of acid and we'll add that to the 25 centimetres cubed of potassium hydroxide, and we'll divide that by 1,000 to give us a volume of 0.055 decimeters cubed. And then we'll be able to work out the concentration of hydroxide ions. To do that, we'll do 2.5 times 10 to the minus 3. That was what was left over from the excess. And we'll divide that by the volume of 0.055 to get a concentration of 0.045 moles per decimeter cubed. So it's worth mentioning here that we don't work out the moles or the concentration of the acid because all that has reacted with the potassium hydroxide, so none of that is left over. So we're now going to work out the concentration of hydrogen ions, and to do that we're going to use the Kw expression. Remember, Kw equals the concentration of hydroxide ions and the concentration of hydrogen ions. So we'll rearrange that, so we've got Kw divided by hydroxide ions, will give us the concentration of hydrogen ions. So the value of Kw is always given to us in the question. In this case, it's 1 times 10 to the minus 14. And we'll divide that by the concentration of hydroxide ions, which we've calculated to be 0.045. And that will be able to give us a hydrogen ion concentration of 2.2 times 10 to the minus 13. All that's left for us to do now is to calculate the pH. And to do that, we're going to do minus log of the hydrogen ions, and that will be minus log 2.2 times 10 to the minus 13, and that gives us a pH of 12.65. Okay chemists, that's it for the walkthrough. There's a link in the description to all the workings that I've done in a PDF file. If you've enjoyed the video and found it useful, make sure you hit the like, and if you haven't already, make sure you subscribe so you get all our videos coming up next week.